Hey, Beth. Nice to see you.
Hey, it's nice to see
Yes. Oh my
you.
God. I saw it was you presenting, and so I was like, I need to chair this talk.
Yeah, when I saw it was you, I was like, oh, that's so nice.
Nice. Very cute. But
Um,
being a chair, I should check the technicalities with you before I
yeah,
engage in asking how you're doing. Do you want to just share your screen? And if you have
yeah.
like videos and sound, we can test them also.
Um, okay, I'll just it's 1:30 a.m. here, just FYI.
Oh, wow. We
So if I'm a little
should have found a different time of day or something.
um how does that look?
I see your slides, not in slideshow mode though, but just yeah,
How's that?
yeah, it's perfect,
Cool.
perfect. And you don't have sound and no video either.
Mm,
Okay, perfect. And also all good with. So you present, we do some group discussion.
yeah,
Carl summarizes in the end, etc.
yeah,
Hi,
yeah.
Anthony. Nice to meet you.
Hi both. Hi Beth.
Hi, how's it going?
Good, thanks. Excited to participate, and I'm up tomorrow. So if you feel like getting up at 1:30 in the morning, Beth, tomorrow, then see you there.
Right. Now that you've already changed your whole.
My body clock, yeah.
Exactly. And did I note down that we should not make the recording public, but you would still like?
Yeah, yeah, if that's okay. Yeah.
Of course, it's okay. So we'll put it on YouTube as unlisted, so only people with the link can see it.
Okay, perfect.
And
Cool.
then we'll send you the link, and then you can do with that what you want.
Okay, great. That sounds good.
Okay. All right. Then I think that's everything. Uh, yeah, that should be everything. I'll keep an
Cool.
eye on the chat, so you don't need to worry about that.
Okay, cool.
And
I'll just move.
also,
How have you been going?
I'm defending my PhD on Friday.
Oh, really?
Yes,
That's crazy. How are you
it's
feeling?
crazy. That's hard to say. I think it takes up most of my mental space most of the time. And that's how it's supposed to be.
Um, because you have a in-person defense, don't you?
Yeah. There's
Yeah.
also an online. If you want, I'll send you an invite.
Oh,
Uh,
really? Yeah, yeah, that would be cool.
all right. I mean, if you're interested, one of my
Yeah, yeah.
opponents is Marta Carrero.
Oh, amazing. Yeah, yeah. I'm doing a symposium with her in 2 weeks.
Oh, exciting. Okay,
Yeah, yeah. I like Mara. Cool.
she's wonderful, and because
Yeah.
she's joining online, we've made it early in the day.
Ah, okay, so then I could join. Yeah.
Exactly, exactly, without having to stay up at 1:30 for one more night this week. Yeah. Yeah. And
Yeah.
then 2 weeks after that, I moved to Switzerland.
For your postdoc?
Yeah, with
That's amazing.
class Stefan
Yeah,
in Zurich.
cool.
Yeah. So lots in my head, but most of them are really wonderful things.
Yeah, that's all so exciting.
Yeah. How about you? How are you? Except
Yeah,
for
I
being
think
up at midnight.
I thought there was no option to change the time. Is that
No.
right? Or
We could have moved it. Carl usually is fine with moving things around a bit if someone's from Australia. So
oh, that's
I'm sorry.
funny. Oh well, it's adding a bit of excitement, I guess.
I guess.
Um, yeah, things are good, just postdoc stuff. But yeah, it's all going along well, so it's good. It's getting summer here now, which is nice.
I wish I had plans to come by Australia anytime soon, but
Yeah, do you think you will? Well, you would?
I mean, I'm sure at some point there would be a conference or
Something, yeah.
something like that for someone to pay me to travel.
Yes.
But I don't have any in mind currently, so it'll be a bit. Yeah. I heard that the CPC conference will be in Yale, so in the US next year.
Ah, okay, because I hadn't seen yet where it was going to be.
I don't know if it's officially proclaimed yet,
Okay.
but I was told so by
Okay. Oh, cool.
by
Will
Al.
you go to that, do you think?
I hope so. I mean,
Yeah.
I collaborate with Al, who's one of the organizers, and so that would be a good Al Powers. So that would be a good reason
Yeah.
to go visit, if possible.
Cool.
Yeah.
We can hang out again.
Yeah, I mean, I guess it's not closer for you, is it, than Europe?
No,
Maybe
no, no. Not close.
because it's the other side of the US. Yeah.
Yeah.
Oh dear. Is there a lot of stuff happening anywhere close to you? Maybe in Australia itself,
I think
or
we have our own like Australian stuff. So we're lucky we've got that, but apart from that, not so much.
nothing in East Asia or something like this?
A little bit, but yeah, also not as much. Some stuff in Singapore,
Ah,
but
right.
it's still not that close.
No,
No.
I guess not. I've only been in Australia once, and I was continuously impressed by how much bigger everything was than my little European head could fathom.
And that's when you met Jakob, right?
Yeah, exactly.
Yeah.
Yeah. I was actually visiting my father, who spent he lived there for half a year or something.
Ah,
But then I
cool.
went by Monash at the same time. Yeah.
Yeah.
Hmm.
Okay.
But do you know Anthony already? Or Anthony?
No,
No.
we haven't met.
Good. I wasn't sure.
No, it's my first time talking to either of you. Hi. I I'm so delighted to have the opportunity to talk tomorrow and to listen in today. But I'm kind of it's not surprising we haven't had the chance to talk before. I'm new to this world. I've been kind of independently for the last year and a half, perhaps, after a career in radio and radar, and then network science and building microbiome host interaction networks. I come to focus on active inference and the mitochondrion. And after a year and a half sitting in my log cabin up here in the Surrey Hills in the UK, not the Australian Surrey Hills,
All right.
I
There's a Canadian
just
one too, right?
what's that?
There's a Canadian one too, I think.
Is that right? Oh well, okay. This is the original.
Okay. Yeah.
Um,
I'm taking sides on this.
I'm sort of airing my ideas in their current form for the first time for the scrutiny of the expert community. So I don't know if I'll sleep very much tonight.
Okay. It'll be a pleasure. I won't be there tomorrow, Anthony, given my defense on Friday.
Yeah, well, I was going to say break a leg, not no luck required, but
Thank you. I can see Carl is here, so I think we can probably start the meeting proper. Hey, Carl, good to see you
Yeah.
or hear you as always. So today, Beth Fisher is presenting her work on reversal learning and neurotransmitters, and I had the pleasure of meeting Beth for the first time this summer. So I'm very excited to be here today. She's wonderful, and despite the fact that it's 1:30 a.m. In her time zone currently, maybe even because of it, I'm just looking forward to the talk. And we'll let Beth talk, then we'll have some time for group discussion, and finally Carl will summarize as best as possible. And as a note to everyone, this will be recorded but not made public. So if anyone wants the recording, they should get in touch with Beth about that. Yeah. If there's no more questions, then there's also no more ado. So I'll leave the stage to you, Beth.
Okay, great. Yeah, well, thank you everyone for having me. And yeah, if I'm at all slow, I apologize. It's 1:30 a.m. in the morning in Australia. But today I'm going to talk about my project I've been working on for my postdoc, which is dopaminergic modulation of model-based reversal learning. And the title is a bit different to what I originally submitted. We don't have the fMRI results ready today to present. But I think that I could actually be good because we can really focus on the model, and then I would be really keen to hear what you guys think about how we could use the model with the fMRI analysis. So maybe in the end, that's for the best. And I'm a postdoctoral research fellow at the Monash University with Jakob Hovey, who I think a few of you know. and the University of Sydney with Clara Callahan. So I thought I would start by giving a bit of background and motivation for the things that, like, what's motivating this project and for a bigger picture and the things that I'm interested in. So I'm really excited about how we can use computational models to understand the mechanisms underlying psychiatric disorders. My PhD was on active inference and optimism bias and how we could look at models of optimism to improve treatments for depression. And I'm really excited about how we can use computational models to better understand things like how different mechanisms might give rise to the same symptom and get more information than you can with traditional self-reports. So that's, yeah, kind of what I'm really excited about. So for my PhD, I use behavioral data to make computational models at the cognitive level. But of course, the next question is, if we have that, how can we connect them to neuromodulators and these systems in the brain? And then if we can do that, then we can have a really big picture of what's going on and just more precise ways of treating psychiatric disorders. So that's what when I finished my PhD and started my postdoc, that's what I wanted to do. And then I started to work with Clara Callahan at the University of Sydney, who's an expert on these systems. And I started to learn that they're not as simple as I had naively assumed. And just like behavior and cognitive processes, they're very messy and complex. So some of the questions that we're thinking about, well, how can we actually link these systems with our computational models? But the overall aim of the research that I want to do is to use these models to improve mental health treatment, so for more precise treatments and diagnosis. So that's kind of the overall aim of the things that I want to do. So when I started my postdoc and we were thinking about what kind of data or what we would need to do to start answering these questions, we realized that it would be really great to get some task-based fMRI. So with that, we could fit the computational models to human behavior and then connect that to the fMRI. And then ideally, if we could get a data set that had a drug intervention that acts on the neuromodulators, we could see and look to see how the changes in neuromodulators that were caused by the drugs, and then look at the changes in the computational model. So that's the kind of data set that we wanted to work on, and this is how we thought we could best answer these kind of research questions. So collecting that data set would obviously take a lot of work, and so I worked with my team to look at what open data set we could use, and we found this amazing data set from Roshan Cools at Radboud University. They have a really great team there, and at the university they have people just dedicated to making sure this is all organized. And I think this is a really good way if we're doing fitting of computational models. There's so much data out there already, and because these are more new methods of analysis, I think there's a lot to be done with open data. So the work that I'm talking about today will be based on this data set, effects of sulpiride and methylphenidate on brain and cognition, a PET pharmaco-fMRI study. So in this amazing data set, they have 100 healthy native Dutch speakers that were the participants. And the aim of their aim to collect this data set is that they were interested in how different baseline dopamine levels could determine how you differently responded to drugs and methylphenidate. So that was the idea of why they collected the data set. So in the design, they have 5 sessions for each participant. They have a screening session, and then they have 3 fMRI sessions and 1 PET session. And with the fMRI sessions, they have a methylphenidate condition, a sulpiride condition, and then also a placebo. And the order of these was randomized across participants. And in the PET session, they use 18F-DOPA to look at the levels of dopamine in the brain. And they also have baseline behavioral battery and questionnaires and structural MRI and cognitive tasks inside and outside the scanner. So I thought before I get in to the details of the tasks that I used, it might be helpful just to talk a little bit about the drugs that were used in this study so we can get an idea at some of the mechanisms that they were looking at. So they looked at methylphenidate, and methylphenidate is also known as Ritalin, and it's a drug that's used to treat ADHD, and also people take it for cognitive enhancing effects. And what methylphenidate does is it blocks the dopamine and noradrenaline transporters. So this acts as a reuptake inhibitor and increases the dopamine and noradrenaline. And it has stronger effects in regions rich in the dopamine transporter. And both the benefits of the drug and as well as the reason the drug can be for risk with addiction issues is because of effects on reinforcement and surprise. And there's some research suggesting that these effects are associated with striatal dopamine signaling. But like with most drugs that we use to treat disorders, there's a large variability in the direction of effects. So for the cognition enhancing effects, for some people it works really well for, and for others it has the opposite effect. And same with ADHD treatment. For some people it's really good, and for other people not so much. So they're some of the questions that the group were interested in. They also looked at sulpiride, and sulpiride is a drug that's used to treat schizophrenia, and it's a selective D2, D3 receptor antagonist. And these receptors are most abundant in the striatum, so it creates enhanced dopaminergic signaling, and then these effects are shown in the striatum where these receptors are most abundant. And the reason that they use sulpiride is sulpiride is understood to have effects in the striatum, and that's quite well established. And that's with methylphenidate, there's different research. Some is saying it works in striatum, others are saying maybe it's more cortical dopamine. So they use the sulpiride as a way to compare the comparison between known striatal dopamine levels and cortical dopamine levels. So that was the idea behind using the sulpiride. So they did a few different tasks in the scanner, but the task that we decided to fit was this Pavlovian reversal learning task. And in the task, there were 2 stimuli per trial. So there's a neutral face and a landscape scene, as you can see on the screen there. And it was deterministic. So if you were in a face reward context, it would be a scene punishment context, and it was the face was rewarded 100% of the time, and then that would reverse. So the way it worked is that they would see both of the stimuli on screen, and one of them were highlighted, and they had to predict whether that highlighted stimuli would lead to a reward or punishment. And this is different to reversal learning tasks that I was more familiar with before, and maybe that would be the same for some of you, is where the outcome of the trial doesn't change depending on what they predict. So they're always going to be in either the reward or punishment trial. They just have to predict if they're in one of those trials. They get told if they're correct or incorrect, but it's different to other reversal learning tasks where you select whatever you select, you get the outcome of that selection. So it's a little different to those tasks because your actions don't have an outcome on if you get a reward or punishment. So the reversal is triggered when there's an unexpected outcome. So if I'm in a scene reward, face punishment condition, and then all of a sudden I see the opposite outcome, that means I've just had the reversal. And the reversals were done after either 3, 4, 5, or 6 correct predictions, and this was randomized. And if they had an incorrect prediction, this would reset the learning count. And there were 3 blocks of 119 trials, so it was 357 trials, and it was around 35 minutes per session. And before we get into the model, I just wanted to show this is one of the papers that they came from the open data set. And what's important to, I wanted to just prime you all with here is one of the results that was found from the task was that the methylphenidate increased the accuracy of the task, and sulpiride decreased the accuracy. And we'll go back to that when we look through our modeling results. So to fit the computational model, there's a few things that we have to think about before we do that. So one of the things is other models I've fitted, there's been action. So I would use the action of the participant to fit to the model, but this model doesn't have any action because the participant is just predicting what they're going to see. So in this model, we actually don't have actions to fit, but we have the outcome. So we can have, for the trials, we can have if they're in a phase trial or a scene trial, if they're in a reward or punishment trial, and if they were correct or incorrect based on their prediction. And yeah, so we can put in their prediction, feed that into the model of if they predicted reward or punishment, or if they were correct or incorrect. And when we think about what's important for this task, so when we're designing the model, we want to think about what mechanisms are important for the task. It's really that, am I in this face reward or scene punishment state, or am I in a scene reward face punishment state? So what reward contingency am I in? And because the aim of this task is to investigate the ability to adapt flexibly when there's changes in this reward and punishment contingency. So we want to make sure that our model can capture that, that aspect of the task. So this is really the change in what state I'm in. So the computational model that we use a variational Bayesian inference model because there's no action. So this is a minimization of variational free energy rather than expected free energy. So I just have this is the equation for variational free energy, and then here we have our message passing, which is leads to our posterior overstates. So when we're fitting our computational models, we want to think, well, what parameters are we interested in? So what parameters do we think are going to be involved in what leads to the different outcomes for the participant? And to do that, we looked at learning of the hidden state factor. So this is the context they're in. And we have here the equation for learning, and it's we have our forgetting rate here and our learning rate here. So we fitted both the forgetting and learning rate. The forgetting rate is just how much I forget my belief about the hidden states from my previous trials, and my learning rate is given my current posterior overstates, how much do I update my belief about the hidden state that I'm in. So it's really this state factor learning of, am I in a face reward scene punishment state, or am I in a face punishment scene reward state? And we can see this in our model here, our hidden state factor. So another thing that we want to do if we're looking at fMRI is we want to have a trial by trial measure for our model. So to do that, we looked at the state prediction error. So this is calculated by the KL divergence between the posterior overstates of the current trial and the previous trial. And we can think of this as the degree of belief updating induced by each new observation. It's also can be called relative entropy information gain or Bayesian surprise. And what it just means is what's the difference between the state I expected and the state I am in. And that can also, in other literature, I mentioned this later on, it can be called state action prediction error, but because we didn't have action, we've called it state prediction error. But also some of this terminology, we're trying to work out the best ways to label these things. So I'm also keen to hear if you guys have any ideas about better ways to label these terms. So the models that I've just gone over, those were our static models. So we also fitted dynamic models, and dynamic models are where the learning or forgetting rate is adjusted based on this prediction error. So again, we have our state prediction error that's calculated by the KL divergence between the posterior overstates on the current and previous trial. And then with that value, you can have a larger value, so it means they're more surprised, and so they'd have a larger learning or forgetting rate. So we fit it, and then this is dynamic models. There's a Anna Sales paper from 2019 does simulations of a dynamic model, and then Ryan Smith's group has recently fitted some data with dynamic models as well. But they all had state action prediction error because their models had action. And this is the equations for the dynamic model. So we have our state prediction error here, and then our learning rate. This is the example for the learning rate model, not the forgetting rate model. Our learning rate, we have a lower bound, and then we have the rate of the learning rate, and that's multiplied by the state prediction error. And then that's the learning rate that gets put into the final learning of the context. So that's the, yeah, I guess a brief overview of the models that we used. And now I'm going to go through the model space and the outcomes of the models that we fitted. So for our static models, so this is when they have the same learning and forgetting rate across all the trials, we fitted 4 different models. We had one with just 1 learning rate and 1 forgetting rate, so that's our 2-parameter model. We had one with where the learning rate was separated for rewards and punishment and 1 forgetting rate. We had another model where there's 1 learning rate and then a forgetting rate for reward and punishment, and then we have one where it's split for both learning rates and forgetting rates. And we fitted these models for each of the conditions, and what we found when we did model comparison was that the 2-parameter model with 1 learning rate and 1 forgetting rate was the winning model for each condition. And then when we looked at the accuracy and the predictability of the model, we got pretty good accuracy and predictability, which was good. So predictability is just how many trials did the model correctly predict that, that the participant did. And then the accuracy is on the trials that they got correct with that value of the posterior overstates. What was that value that they were in the state that the participant predicted they were in? So that's our accuracy measurement. We also fitted 2 dynamic models. So we had a dynamic model with dynamic learning, and then we had a dynamic model with dynamic forgetting. And we found that the dynamic learning model was the winning model for each condition again. And then we had good accuracy and predictability for that model as well. So even though our model has, so it's got good accuracy, it's got good predictability, and it, it's got, with the model comparison, it looks good. Another really important step is the recoverability. So with the recoverability, what you do, you have your fitted parameters. So I have my learning rate and forgetting rate for my participant, and then I simulate a whole new set of data based on that forgetting rate and learning rate, and then I refit that simulated data to get parameters out of that simulated data. And the idea is that the parameters that are fitted from the simulated data should be really highly correlated to the parameters we use to simulate that data that were fitted from the participant. Because if those parameters are highly correlated, what that means is that those parameters are telling us something specific about that participant. If you simulate data and then you get parameters out that aren't highly correlated, what that can mean is that a range of parameter values can generate that same behavior. So perhaps those parameters aren't telling us something very specific about that participant. So it can be a question of what we're gaining from the model. So for our static model, we did the recoverability of the learning rate and forgetting rate for each condition. And yeah, so we get really good recoverability, which we're really happy about. So this shows that our parameters are telling us something specific about the participants. And then when we tried to recover the dynamic model, we couldn't recover the model. And I just wanted to go through this because it's kind of a nice demonstration of when something doesn't work, but it actually is telling us something interesting. So when I tried to recover the parameters, there was really low correlation between the simulated and fitted parameters. And then what I looked at, so what you can do is you can say, well, in my model, my parameter space for the model, are any of the 2 parameters in that model in that parameter space correlated? And what we found was that the learning rate, the lower bound for the learning rate, and as well the learning rate of change, those 2 were highly correlated in the fitted model. So what this might suggest is that the dynamic model had a redundancy in the model structure with these 2 parameters. And it could suggest that they're capturing an overlapping aspect of the underlying cognitive process. So if you were to do this, the next step would be, well, can we combine those parameters to 1 parameter to make, and maybe that will mean then we can recover our parameters out. And what's cool is that that's actually what the static model was. So in our static model, we have the 1 learning rate, and that is basically the thinking about how we could combine those other 2 parameters as just 1 learning rate. And then if we think about why this could be, so why did we get this result? if we think about the task is, it's quite simple. So you really just have to, when I get something unexpected, I need to change my prediction. So maybe in a task like this, having a dynamic learning rate that might be, that's tracking like volatility in the environment and these kind of things, you might not need that for a task like this. So it could make sense that that's why this dynamic model didn't recover. So now I'm going to go over the model results of our static model with the one learning rate and one forgetting rate. And I'm going to go over 3 different sets of results. So I will look at the results of the individual model parameters, and then look at the results of the state prediction error, and then we're going to look at the results of the parameter space. So this is the results of the learning rate. So what we can see here is the methylphenidate increased the learning rate. And we can also see here that the methylphenidate also really homogenized the performance. So if we look, you can see in the plot that the methylphenidate meant that the learning rate was much less variable, and most of the participants came to have the same learning rate level. And then if we think about the outcome of their behavior of the task, and we remember that methylphenidate improved the accuracy. So the participants when they were in the methylphenidate condition, they had the highest accuracy. And when we think about the learning rate, so the learning rate is like when I have my how much I'm learning from my new posterior overstate. So how much am I updating my model based on that? And if we think again back to the task, this does make sense that this is the best strategy in this task, because all I need to do is when I see something that I don't expect, I should change my prediction. So thinking through kind of the mechanisms behind this, it makes sense that methylphenidate would increase learning rate, and that improves accuracy. And we also found that the sulpiride decreased the learning rate, and that was lower than the placebo. And again, if we remember in the behavioral results, the sulpiride did decrease the accuracy. These are the results for the forgetting rate. So we found that the methylphenidate had the highest forgetting rate and the sulpiride had the lowest forgetting rate. These values, the changes are significant, but the changes in values are very small. But what this means is that when they're in the condition with the sulpiride, they were just making their predictions based more on things that had happened in the past. So they were just their predictions were based on things that they'd seen in the past, and less on the new observations coming through. So that's the difference of what's happening with the sulpiride and the methylphenidate. So then we looked at the state prediction error differences, but for these reversal trials, because they're the trials that are important with this task. So what's this kind of surprise that they had when they get the unexpected outcome on these reversal trials? And again, what we can see is our methylphenidate increased the state prediction error for the unexpected outcome. So when they got something unexpected, they have this larger state prediction error. And this follows with this ability to flexibly adapt behavior to new reward contingencies. Because if I have this higher state prediction error, I'm going to be like, okay, I'm got to predict something else for the next trial because something has changed, and then my model is able to incorporate that change. And then we can also see that sulpiride decreased the state prediction error for the unexpected outcomes. So they're the results for our individual parameters and the state prediction error. But one of the things that is really like powerful and I think is really cool about computational models is that you can look at the parameter space change. So you can look at how the parameters change together rather than the individual parameters. And again, this is kind of the power of computational models, because you can look at multiple computational factors and how they jointly impact a patient's decision making. And this allows us to have detections of differences that you might not see with other methods of analysis, because there could be small shifts in each parameter that lead to a large change in the parameter space. and it helps us reveal subtypes of disorders and transdiagnostic phenotypes. So we just have a figure to illustrate this here. So imagine you have a model that is 3 parameters, and you have your 2 participants sitting here in the parameter space. So these are the values for their 3 parameters. And then they have this intervention, and participant 2 is really shifted to a different location in the parameter space after the intervention. So now what I'm going to do is look at the parameter space change for the learning and the forgetting rate for our model in the 2 different drug conditions. So how we've shown this here is we did a density plot of where the participants fell on the parameter space, and then we subtracted that so you can see the difference in parameter space from methylphenidate and placebo and sulpiride and placebo. And here we have, this is a vector shift of what happened with the parameter space. So the white here is where the highest density was for the placebo group. And then we can see this arrow has shifted the density over here with the methylphenidate. And then we can see the same for sulpiride. But what I like about this figure is that you can really see that what the methylphenidate has done has shifted everyone to basically the same location in the parameter space. So we can see everyone's brought up to this corner, so it's all in the same direction. But then when we look at the difference between the parameter space between the sulpiride and the placebo, here it's more variable, so you don't see that same shift, and there's kind of a spread. I think this is a nice way to visualize this, and hopefully this can also show how the parameter space can just give us more information than looking at those individual parameters. So the conclusions, to sum up what I've spoken about. So the increased dopaminergic activity from methylphenidate improved the reversal learning, and this is shown in the model of the ability to flexibly change behavior. And the methylphenidate really homogenized the performance of the participants, so it changed their model and parameter space to all a very similar level. So we can think, well, then what might this mean for methylphenidate as a drug in certain contexts? What contexts would this change in parameter space be a positive thing, and when may it not be a good thing? And if we think about back to the introduction, how one of the issues with methylphenidate is for some people it's really positive, and for others not so much, can maybe understanding if it shifts you to this space, can we maybe understand why some people that might not be so positive for, and or what their parameter space is before they have this kind of drug. So yeah, kind of thinking about what that can tell us about that. And I've presented this work to people, some clinicians who work with ADHD, and they said it will be interesting to think about the relationship to existing literature on set shifting in ADHD, which is this ability to change, basically flexibly change your attention and what you're doing. And methylphenidate is meant to help with that. So can this kind of model give us more information to what's going on there? And then also this data was collected in healthy participants. Could we now collect some data in a clinical cohort to see how it shifts the parameter space with people with ADHD? Another thing that after the fMRI, what we'll do is, because we have the baseline, we have the PET scans, we can also group the participants into their baseline dopamine levels, and it will be cool to see based on that, well, what was the parameter space change or shift based on your early dopamine levels, or your baseline dopamine levels, sorry. Another thing, and I'm curious to get your opinions on this, is, so we see that the state prediction error is higher for the unexpected trials with the methylphenidate. So what kind of relationship can we think about the dopamine has in the state prediction error, and is dopamine helping? Yeah, what is that relationship in the brain with the state prediction error and maybe dopamine? And hopefully when we get some of the fMRI, we can also start looking at that because we have that trial by trial measure. Yeah, and this is, I guess, just what I said. So we're going to be doing ongoing work to apply dimensionality reduction techniques on fMRI, bulk data, and establish the low dimensional brain-wide signatures associated with these state prediction errors. Yeah, so thank you. This is my group at Monash, and then these are the people, my group at Sydney. So I just wanted to thank them as well. But thank you for listening.
Thank you so much, Beth. That was wonderful. Let's, as is our custom, all unmute our microphones and give Beth a round of applause. Thank you. All right. Now we have some time for questions and comments from the audience before Carl summarizes later. And
Should I stop sharing or should I keep my slides up?
You decide. So someone might
Okay.
ask something about the slides, but you can always just share your screen again if it comes
Okay,
up.
I might stop for a second. Yeah.
And you can see us properly, right?
Yeah.
So I think that's valuable. And so I certainly have quite a few thoughts. You also hit me just as I've finished writing up my PhD thesis on similar topics. So kind of it's bristling in my head as we speak. So that's exciting. But I will also just keep an eye on if anyone raises their hand or writes in the chat, and then I will make sure not to spend all of Beth's time on my own questions and comments. But while people are just gathering the thoughts, maybe I can bring up one or two of them. And then you can see if you think they're useful, Beth. That's so one thing was on the actions, one thing was on relating it to brain data, one thing was on the fitting methods, and one thing was on the modeling. These were the things I had some stuff in my head. But I also just wanted to say that parameter-based stuff is very exciting. So, I make software for these kind of analyses, and maybe it would be nice to have some default plots that people can just use like this. So
I think that's a great idea. And I'm also excited because was a 2-parameter model. I think it'll be really cool to get 3-parameter models, and then you can have a 3-dimensional space. You can imagine like some cool shape. Yeah, I think that's I'm kind of excited to do that. And I think that would be cool if you're making some software, we could do that.
That's exciting. And of course, as soon as you get more than 3 parameters,
yes,
do like pairwise or something like this. All right. So thought number one, I would usually in my own work call it an action when people make an explicit prediction about what happens on the next time step. I don't know. Sometimes I call it a report action where they just report a belief. And of course, in one subset of models, and that includes some of the models I work with, you only have a perceptual Bayesian model, just like in your case. And then you have to find some way of transforming that perceptual Bayesian model into some behavior, because otherwise you can't fit it. And that's exactly what you've done. But I would usually call that actions also. And I'm sure you could, in principle, do that with an active inference model, where you have preferences for making like spitting out actions that then correspond to the observations you get in the next time step, etc. It might not change the model predictions very much, and it could be a bit complicated, but in principle, that should be doable. And maybe Carl, thoughts on this? I'm trained in the HGF, and that's a different only perceptual model currently, where we do the same thing. Then you just use some reported belief about as their action, basically.
So we spoke a lot about this when we were designing the model, and because I'm also working with Chris White, I'm sure a lot of you also know, and so we went with the no action because the prediction of the participant doesn't really change the generative process because you're not getting. And so what matters is the reward or punishment, and that's not changing. So it's not like if so we thought if we fit a model with action, you want your action to then change the structure, and it's not doing that. So what we did is we still, we had to do some, so we fitted in, what we did is we still, the outcome of correct or incorrect could change. We did we fiddled around with the code a bit, so that could change, but that was just depending on the participant's prediction, which we coded into that posterior overstates. So we just put it all through that rather than the action. So the outcome of the the outcome of the generative process never changed, and we just fed in this posterior overstates, which was the prediction in. So we had to do some things to change it around, and I can share with you the code. But after a lot of discussion on what we wanted to model, we thought that was the best way to do it. Because in Pavlovian reversal learning, that is what is happening.
Yeah. So one thing is technically implementing it. Another thing is conceptually, people do, of course, produce an action that changes their observations insofar as they observe their own action.
Yeah.
So I would, I don't know, personally, I would conceptually definitely consider it an action to make an explicit prediction.
So, but then would you think, so just say you're doing a like a two-arm bandit task, how would you then differentiate this Pavlovian reversal learning from a traditional two-arm bandit? Because they are very different. So I guess, yeah.
So in a bandit task, your actions can change whether you get rewards or punishments.
Yeah.
And in this case, your actions can only change whether you observe yourself predicting.
Your actions can only change whether you observe yourself predicting
A or B, and then you get your reward based on whether your prediction, which you observe, fits the outcome. I don't know if anyone has actually used this for with a full active inference model. So maybe Carl will know. In my work, we also do this. In my work with the HGF, we also do this stuff where you just take the prediction out of the model, and then you have a separate response model that produces the action based on that. And I would say that's exactly what you.
Yeah, that's it. Yeah.
So that's the Jean Denisot has this paper called "Observing the Observer," where they make this distinction between perceptual and response model. And I would say in active inference, they're more intertwined.
I suppose the other thing is, and I don't know what you think about this, but because, we really thought a lot about how we wanted to structure the model and the mechanisms of it. And then because we got such good modeling results out, that gave me confidence. I think if I had done all of that and then we got bad recoverability and predictability, I would have been like, oh, we're missing something. But then I kind of like to go with, okay, well, we got this result out. And then we didn't for the dynamic model. So it kind of, that I feel like gives me also confidence that perhaps not having the action is capturing something meaningful.
And I mean, it's purely a conceptual thing to me.
Yeah.
That
Okay.
making an explicit prediction that affects your reward, depending on whether you're right or not, I would always consider an action.
Yeah.
But it might not be modeled with the same machinery we normally use to model actions in active inference.
Yeah.
And so, I mean, it in a way changes the model. Even if you did implement it with the same machinery, you arguably get the same thing out, just more complicated to implement.
Yeah, and we'd have to think about preferences and these kind of things, and we don't with this model. Yeah.
Exactly. So you could of course have one where you have preferences for rewards, and you only get rewards when your prediction
is correct.
Yeah, exactly.
Yeah.
And then you actually are, the loop is complete.
Yeah.
But so that was mostly a terminological thing, I suppose, or a conceptual thing. And again, we'll see what Carl thinks of this also. Then, what were the other things? Yes, one was the brain relatedness. And just, I'll mention one more time, Anthony and Carrie and so on, just raise your hand if you have questions and comments. I'm sure I can also find other times to talk to Beth if she wants. But for now, I'll just briefly bring some stuff. We can also talk more if you want. So on so basically, the standard as I know it in the field and I expect that's also what you anticipate doing, is have your behavioral data fit your model, extract some stuff, and it could either be stuff that varies trial by trial, such as prediction errors or predictions or beliefs or uncertainties. So there's quite a few things you could drag out. Or it could be stuff that does not vary trial by trial, and so that could be your learning rates and so on. And then simply using those extracted belief states and parameters as predictors in your neuroimaging analysis. And if you do that in DCM, I forget the name, but you have ways to do that in DCM. You have ways to do that in any kind of neuroimaging analysis. And that's useful and exciting. Also, sometimes what you would do, if you just get out a baseline dopamine level, you can that's just one variable and just correlate it with what you have. I know, so I just wanted to mention this, not necessarily to suggest you do it, but I know there are people trying to instead make a joint model, the cognitive model and the model of the brain dynamics is one model.
Oh, cool.
And fit it to the behavior and the neuroimaging data at the same time.
Oh, what? Who's doing that?
I have some articles I can send you. There's a book.
Yeah, that's super interesting.
It's a book called Model-Based Computational Cognitive Neuroscience.
Okay.
Which is and so these are people who come from the mathematical psychology world.
Yeah.
And so that's the old school cognitive model people who don't usually do that much active inference, but they have the same agenda otherwise. And then your neuroscience people coming together there.
Cool.
And there's some papers where they discuss different ways of doing this and the relative difficulties and advantages. And one difficulty is that it becomes a big model very quickly. But I mostly wanted to mention it.
Yeah.
And I wanted to suggest also using other states than just the state action or the state prediction error. Just because in the work with the HGF, we also have prediction errors, but there's also how certain you are about your prediction. What is your prediction, etc. Maybe you're free or you're surprised. And it's not always the prediction, sometimes it is, but it can also be some of the other things that relate. And I don't know enough about neurobiology to have strong predictions here. So you will know more about that than I am, but they can all be plucked out, I'm sure, from the model.
Yeah.
Yeah.
Yeah, no, that's a good point.
Yeah. Okay. I'll send you that paper, and then you can see if it's interesting. But it's nice to know that it exists, and maybe Carl has some thoughts also on this.
Cool.
Then next thing, if you think this is useful.
No, this is very helpful. Yeah.
So very similarly, in the same way that you can first fit your cognitive model, extract some stuff, and then correlate it with brain data. That's also what we do when we look at differences between clinical groups or interventions, or some of the other maybe questionnaire data you also said you had. The cognitive model separately, drag out, extract the estimates, and then correlate them with stuff. But in the same way, there are people who would put those two things in one model.
Yeah.
So you estimate the parameters while estimating the relations to external variables of some kind.
Yeah.
And the advantage there is that you don't lose the information that you otherwise do when you pull out just a point estimate from your posterior over a parameter.
Yeah.
You lose the uncertainty, and the parameters will constrain each other. So it's a kind of hierarchical model, actually.
Yeah. Okay.
It means that you have the two group and you have the differences, and your knowledge about the other members of your group will also influence the estimates. So the cognitive parameter estimates for each participant will depend on the other members of that group. And that has been shown to recover a lot better and more accurate.
Yeah.
The downside perhaps is that you can't compare it as easily with results from other data sets. But at least in the cognitive modeling, well, I know these kind of hierarchical models are considered the gold standard.
Yeah.
So I just wanted to say that's also an option out there. Again, the downside
cool.
is that it becomes a big model. And Yeah, I just wanted to mention. Yeah. Okay. Then the last thing. Yeah, I just wanted to say also, I don't know enough about the dopamine stuff to have a strong prediction. You were asking about it, and there I can't help so much.
Yeah.
So the last thing was on the modeling. So you're using this. You have the POMDP,
Yeah.
or I guess in your case, because you don't model the action selection as part of the variational inference, it's just a hidden Markov model, I guess, if I'm not mistaken. So you have observations and there's some stuff and it changes, but the belief updates are the same.
Yeah.
And then you have parameter learning on it. And here I hope Carl will correct me if I say something wrong now. But the parameter learning, so the standard parameter learning, you just count.
Yeah.
And the learning and forgetting rates have been added by Ryan Smith and others.
Yeah. Yeah, that's right.
So the standard just counting, that's the kind of Bayesian inference method in a stable environment, if you assume the environment is stable.
Yeah. Yeah.
Of course, the environments are not always stable, and specifically in your case, they're definitely not stable.
Yeah.
And therefore, the learning and forgetting rates have been added, as I understand it, as kind of a shorthand for a different generative model where you expect the environment to sometimes change.
Oh, I actually didn't know that's why. Okay, I understand, but I actually didn't know that makes sense.
And
That's why
so
I got it.
I've discussed this with Ryan a bit, and I think it's accurate to say, but I'll defer to Carl or Ryan or others if they have different opinions.
Yeah.
I just wanted to say. Because exactly like there are old results in the reinforcement learning world, because notice the Dirichlet updates actually look very much like a Rescola-Wagner update or something like this. And there are old results showing that the learning rate that's optimal depends on the volatility of the environment.
Yeah.
So in that way, it's perfect to fit those parameters because you have a volatile environment, and the question is whether people catches on to it being volatile.
Yeah.
And adjusts their learning and forgetting rates. And I think these dynamic models, and that also actually exists in some of the old reinforcement learning models, where you make that learning rate depend on something, usually the prediction error. And that, in a way, as I understand it, is also a shorthand for, I got a high prediction error, so the world is more volatile than I thought. So I need to up my learning rate a bit.
Yeah.
And so in that context, I just want to mention that so models like the HGF they can only do that, so they don't do actions. There are many things they do not do, but the thing they are specifically made to is the learning in environments that may change.
Yeah.
And I mentioned just because, so you can plug an HGF on top instead of the Ryan Smith style updates.
Yeah.
You might get more or less exactly the same behavior, just with a more complicated model. So I'm not necessarily advocating for it.
Yeah.
And we haven't tested it much, etc. I've run it, and it certainly works. But
that's what you guys are working on?
Yeah, that's one thing we're working on.
Yeah.
So I mostly just wanted to mention, in case you thought it was.
No, that's No, it's very helpful to because obviously sometimes you just don't hear about this stuff, so it's very helpful to hear what's going on. Yeah.
And the one reason I thought it might be interesting is also because you found that if I understood you right, that in the dynamic models, the effect on learning rate and effect on forgetting rate were not identifiable.
Yeah,
So they were
exactly.
highly correlated, and you couldn't know which of them were causing the behavior.
Yeah.
And the reason I thought it was just because in models like the HGF, the learning rate is a direct function of your uncertainty, relative uncertainty between your prediction error and your prior.
Yeah.
As in, I think in general in Bayesian inference. And the relative uncertainty is also not only, but to a high degree, a function of how volatile you think the environment is. And so that to me just means that probably they're unidentifiable because they are shorthands for the same thing.
Oh, I see what you
That's
mean.
my guess. That because both increased forgetting and increased learning rate reflect a belief that the environment is more volatile,
Mm.
of course they're correlated. That's my intuition, at least. I'll defer to Carl and others, but that's my thought.
With the dynamic models, though, it was only dynamic learning and dynamic forgetting. So for the dynamic learning, we did just have one parameter for forgetting, and it was just the two parameters that were changing the learning rate. They were correlated.
And which two were these?
It was like the lower bound on learning rate, and then the learning rate that's multiplied by the state prediction error.
Yeah, so the
And that,
effect of the prediction error and the lower bound.
yeah,
were
exactly.
correlated.
Yeah.
Yeah.
And that's why I thought, oh, well, maybe that's because it's just such a simple task. It doesn't make sense to have, yeah.
So I guess this when you have when you have unidentifiable parameters, it's either it can either be because your task doesn't let a participant produce
Mhm.
behavior that would distinguish
Yeah.
between them, but it can also just be because it's two parameters that reflect the same thing.
Yeah.
Uh,
And
and my
yeah.
intuition is but again, maybe there are other tasks where they are distinguishable, and Ryan Smith would know, you would know.
Yeah, I see what you mean though. Yeah.
Yeah.
Yeah, cool.
So there's a lot of blabber, but maybe
No, it's very helpful.
yeah. That's probably it for me for now, at least. Except there was, yeah, no, it was just that when you were showing the results, that the difference in performance when you gave people the drugs,
Yeah.
interventions, seemed to be due to a difference in learning rate.
Yeah.
That seemed to make sense to me, given that the task is a task where the main task here, it's learning the probabilities, but because it's a reversal task, the hard part here is adjusting your learning rate.
Yeah, I think it also makes, well, the way I was thinking about it with the learning and forgetting is in this task, the best strategy is to just whatever you, so if you make a prediction that's wrong, you just change completely because it's deterministic.
Yeah.
And to me, that makes sense. Then you should learn most about your
Yeah.
most recent posterior over state, not, remembering, oh, what was my, long-term beliefs about my hidden state
Yeah.
factor. So I thought that made sense that the learning rate correspond to accuracy for a task like this.
It's basically a task where higher learning rate is better.
Yeah, yeah.
So the situations where high learning rates are not so good are situations where you have noise.
Yeah.
So where you get a reward, but it's not because the probabilities have changed a lot. It's just because you get a punishment, but it's not because the probabilities have changed. It's just because sometimes you get punishments.
Yeah.
And
Yeah,
you don't want
exactly.
your learning rate to be too
Yeah.
large. So it might be that there are tasks where the disadvantage of too high learning rates are stronger.
Yeah.
And then you might not necessarily see this increase in learning rate corresponding to increased accuracy so much.
Yeah, no, 100%. And I think that's also when thinking about, methylphenidate, like this task is a very simple task. It's asking to do a very simple thing. And how does that actually apply to other contexts and environments? It's so you also have to think about it, because I'm interested in, well, how can these models, what can they tell us about mental health and the real world? Yeah, this is definitely a task. It's like, well, what situation, what are we actually modeling and capturing, and in what environments is that adaptive to do? Yeah.
But I mean, the work is brilliant. So it's very elegant, very thorough, careful, like good cognitive modeling work. Like, so it's a huge pleasure.
Thank
These are
you.
like little.
Thank
Yeah.
you.
Oh, last thing I want to mention. It's also just because I've just been reading up on it. So you did parameter recovery, which is
Yeah.
wonderful, and many people do
Yeah.
not. I just want to note you can also do model recovery,
Yeah.
where
Someone
you
had mentioned that to me recently. Yeah.
which is just simulating behavior from different models, doing model comparison and seeing if you get the right models back. So you can have, just like you can have unidentifiable parameters, you can also have unidentifiable models. And to the degree
Yeah.
you're interested in model comparison, that can be useful.
Yeah. Do you think that it really is the standard of, showing evidence for your model, you should do model recovery and parameter recovery? Because
And
I
you,
haven't seen model recovery as, like, I haven't come across that as much as a few people have mentioned. Yeah.
it's newer, it exists. I think
Yeah.
it's less common. I would say it's good. So
Yeah.
I mean, in a way, choosing between models is not that different from choosing between parameters
Yeah, no, that's true. Yeah.
from a Bayesian perspective, right?
Yeah.
So
Yeah.
Paul will maybe have thoughts on this also. So I mean, I would and note that there are they call it something like landscaping, but basically they make the point that model recovery will depend on the parameter values.
Okay.
So if you choose to do model recovery, if you want to be like completely thorough,
Mm-hmm.
you should really do model compare, like basically do your parameter recovery within each model comparison or each model.
Yeah, I see. Yeah.
Again, it becomes large, but
Yeah.
that would be the comprehensive version, yeah.
Yeah, but that's good.
And similarly, you might be interested also in running some prior and posterior predictive checks.
Yeah.
Just these standard kind of
Yeah.
methods for this.
Yeah.
Yeah.
No, I
And
think that's great.
there are more than these actually. I have a list, but I think these are the main ones.
Cool. No, that's helpful. And yeah, I think you're right.
Yeah. I mean, that's why not in a way.
Yeah. Yeah, exactly. Yeah.
Practice, right? It's not that I would expect everything to look fine. I think that
Yeah.
has been done with similar models and similar tasks many times by now, but it's all just nice practice.
It's always good. Yeah.
Okay, so that was a lot of blabber from me, but
That's good. Thank
you
you.
right in my homeland, so that's nice. And we can just stay in touch if anything comes up.
Yeah, awesome. Great. Thank you.
Yes, and all this was recorded, so you have a free notes in that
Cool.
way, which is especially with Carl, that's useful sometimes when he talks fast. That's good to have a recording afterwards. Okay, so I'll just give everyone a chance to ask questions or just bring comments in general. They don't have to be modelers' questions or comments. That was just my perspective, as usual. So I'll just give just a few seconds. If anyone has questions or comments, they can raise their hand. And now. And otherwise, I think it is your turn, Carl.
Is it my turn now?
Indeed.
Yeah. I switched my camera on and I will speak quickly because it's probably now about 2:30 in the night time in Australia. So if you want to go and have a nap and then listen to the recording later, that's probably the best thing to do. Right. So yeah, excellent presentation and clearly an enormous amount of work. So I'm going to limit my comments to the discussion that you've just had with Peter. And then just highlighting a few historical papers that would lend power to the way that you've already done it. If you get reviewers who say, "Oh, you can't do it like this," or "There's no precedent," and then thirdly, another way of looking at this problem, which addresses some of the issues that you've been talking about, and probably speaks to your machinations with Chris about, what is the structure of the generative model for this kind of behavior. So that will be revisionary and possibly future pointing if you want to proceed down that down the avenue that I'll describe at the end. But just to come back to some of those key points that you were talking about. What was the last one you were talking about? Oh yeah, model comparison, parameter recovery. From my perspective, it's probably in terms of model identifiability, the normal way of doing this outside computational psychiatry and and the neurosciences or cognitive modeling probably it would be to do to construct confusion matrices using synthetic data, so that you have a number of different models and then you generate as many data sets as there are different models, and then you invert all of the data sets with all of the models. So you now have a number of model times number of model matrix that you populate with the elbow or the variation free energy or the log evidence, and then you softmax it, and then you have a series of columns. And what you're looking for, if you've generated your data in under appropriate assumptions about the signal to noise, for example, then what you're looking for is recovery being that the winning model is on the leading diagonal.
Yeah.
That implicitly tells you your parameter recovery is okay. You don't.
Okay.
So what I'm trying to say is that there's certainly a meme around at the moment that a good paper has to have parameter recovery. It does not. What you need to establish is the model identifiability. Having said that, sometimes it is useful to disambiguate potential partial conditional dependencies between parameters if you want to sort of wax lyrical about one particular parameter. So if you want to pick out one particular parameter from a posterior density and correlate that with some independent behavioral score or drug condition, then you may want to assert that this is not correlated. It doesn't have conditional dependencies with other parameters. So you can look at the posterior covariance matrix or the posterior covariances amongst parameters under the winning model to justify that, but it's not necessary. If you can't recover your parameters, you can't disambiguate between models. So that, in a sense, that the model is basic. The difference between models is that parameter necessary or not, because this model differs from this model because it doesn't or does not have this parameter. So if you have a slight skepticism about parameter recovery, then certainly indulge it. Having said that, that has become the millennial meme this decade, and therefore there are people who are ideologically committed to including and also insisting on the inclusion of parameter recovery, but mathematically it's not necessary. The key thing is the the model identifiability, which is accessed in exactly the same way that you've done it. It's just that you just generate lots of data under different models and then create a confusion matrix. The issue about having one big model for both the behavior and the physiological responses, that was a very interesting discussion. I can see the benefits of that. Having said that, the advantage that Peter was talking about in terms of resolving conditional dependencies between the parameters of the observation model for your behavior and the parameters of your observation model for the, say, neurophysiology, fMRI or EEG or whatever, they have to be shared. And in most instances, they're not. In most instances, one kind of data informs or shrinks your posteriors over one set of parameters, and then the other kind of data shrinks your posteriors over another set with very little overlap. So what that means is that instead of having a very, very big model, what you can do is just implement Bayesian belief updating by doing it sequentially. So if there is any overlap, you first of all take your model appropriate, say, for explaining the behavior, you invert your model in the usual way, and you now have posteriors over the parameters. And then having done that, you then use the posteriors of the parameters that are shared in your second model, say a model of MEG or fMRI, and use the posteriors from the first analysis, the behavior analysis, the cognitive modeling that you've already done, as priors over the parameters of the second analysis, so that now but your second analysis will have another kind of generative model with parameters that weren't in the first kind, but you can still inform the estimates of the second parameters by using this notion of Bayesian belief updating, in the sense that yesterday's posteriors are tomorrow's priors, and just accumulate by successively accumulating different modalities of data. But it does depend upon there being an overlap. So you actually have to have a generative model of fMRI that was actually generated by the parameters that you're estimating with the behavioral data. Usually that just simplifies to sort of picking out sort of proxies for this or proxies for that, or testing different hypotheses. But again, just standing back, the notion of what's called sometimes called Bayesian fusion, where you're fusing different modalities under a grand model where there is some intersection can be addressed using just simple Bayesian belief updating, using this notion again of yesterday's postdays are tomorrow's prize. What was the other issue you were worried about, Peter? Can you remind me where did we start?
The actions.
Yeah, absolutely, yeah. So actions, yeah, I can see that, and I think I can see both choices and the motivations for both choices. But I would. If you want to do it the way you've done it, I think you're perfectly licensed to do that. On the other hand, if you want to do it in the way that Peter's suggesting, you're also perfectly licensed to do that. And I think if you had to explain yourself to Jakob or to Roshan or whoever, then you can say, look, there are two ways we can use Bayesian beliefs in our in our model of this particular subject. We can either use those beliefs to evaluate the most likely action using expected free energy in the usual way, and then use the recorded behavior of this subject in order to identify the most likely beliefs. Or we can ignore the behavior and just assume that I'm dealing with the Bayes optimal actor under some under some hyperpriors, and use the posterior beliefs directly to report what this subject is believing, so that the action now becomes, well, if the subject had actually behaved to report their beliefs, they would do this, but I know what they would do because I know what they're currently believing. I believe in that I'm in the first context and not the second context, for example. So I think you're licensed just to take the posteriors over the context state as a proxy for the internal belief state, and then everything else that you want to do that, which should give you similar kinds of estimates of the parameters of interest. Had you actually model all the detailed, I'm going to predict it's going to be a reward. It would be easy to do that. So in the context of active inference, you just actually set up an active inference scheme where the subject prefers to get correct as opposed to incorrect. So they are just, so in one sense, this is just a volatility paradigm where you're asked to predict what's going to happen next, and you want to be right. So, and in that sense, wanting to be right is the reward, getting it correct is the reward. But it's also slightly simpler than that. But you can put preferences in and get purposeful behavior, correct pointing behavior, simply by simulating the behavior under the assumption that the agent wants to be right. Notice there's an interesting twist. It's got nothing to do with your presentation, but it's an interesting twist. Sometimes people will deliberately choose the wrong response because of its epistemic value. Sometimes there are certain situations where they get more information by deliberately choosing the wrong response, just to make sure that they, in some instances. So once you've got the full active inference scheme in play, you can sometimes with more complex generative models get interesting behavior, even when you prefer to get correct versus incorrect. Sometimes deliberately soliciting an incorrect response just to check that things haven't changed is sometimes the Bayes optimal action under the sort of principle of optimal Bayesian design, implicit in the expected free energy. So you could have built a little active inference agent who actually chooses to predict reward or not reward, and actually simulate the whole action selection and the reporting of the prediction, should you want to do that. So but you don't have to. In many instances, you can just, especially in the context of subjective reporting, say metacognitive studies, you just make the simplifying assumption that you have privileged access to this person's posterior beliefs just because they're a human being, which you wouldn't have if they were a microbe or a laboratory note. And then just use that directly. Excellent. So I'll quickly, bearing in mind you probably need to go to sleep soon, I'll quickly share some papers which will remind me to feedback on the stuff that you've done, which just to fully endorse that, and stuff which you might want to do as an alternative to the current approach. So I'm sharing my screen. Oh yes, I have to actually share it, don't I? Very good. Oh yeah. So this is, if you're interested in the more general notion of how do you accumulate evidence from different kinds of data in the service of building or inverting a generative model of everything. This is a very common problem, and of course, one of the key problems is trying to fuse electrophysiological and hemodynamic data, for example. In your case, it's behavioral data and fMRI data, but the principles are exactly the same. This is a really complicated paper, but it's just nice because what it allows you to do is just to assess the information gain afforded by different kinds of data. So in the context that there are some sort of shared parameters between your two models, then you can measure the degree to which you first shrink it with the first kind of data, and then you put the second kind of data in and you shrink it a bit more. And each shrinkage can be measured as a KL divergence or information gain. So you can measure the information gained as you go through different kinds of data. So some data are very good for these kind of parameters, other data are good for a different set of parameters. And it's quite interesting just to see how different kinds of data inform different kinds of parameters. I should say, I repeat though, usually what happens is data kind one, so the behavioral data, shrinks or increases the precision of your posterior estimates of one set of parameters, and the next kind of data, the fMRI, is a completely different set of parameters, which means that you don't need to do this usually. And usually it's the kind of parameters you get from fMRI is where in the brain is it. So there's nothing in your active inference model or your reinforcement learning model that parameterizes where in the brain it is. So there's nothing useful, if you like, that is usefully shared when it comes to your fMRI. You just sort of take the what is being represented from the behavioral data and pursue that. Where is it with the fMRI data? Probably not quite the same for electrophysiology, but certainly for fMRI. So that was that one. Yes, and that's just the original one. Oh, good grief, my apologies. Yeah, just to so these this you framed it as a reversal learning paradigm, but of course there isn't, as you say, any reward, so it's could also be cast as a volatility paradigm. That I think was the perspective that Peter was taking, and of course this is being covered from many directions under the notion of hierarchical Gaussian filters. Had you considered using a hierarchical Gaussian filter? Is that a community which you knew about?
I don't really work with anyone who uses it or anything, so I hadn't really considered it. But now, after speaking to Peter, I think, yeah, maybe we could do that.
Yeah, well, you could. That would be one direction. It's not what I'm going to suggest you do, but that would be. You can look at this hierarchical Gaussian filter as a little bit like a generic active inference scheme, but with a special focus on estimating the precisions and doing so in a hierarchical sense. You're talking about the precisions of the precision. So Peter was saying before, it's not just about how confident am I that the context is going to change. It's, how confident am I in that confidence, and so on hierarchically. The slight problem with the hierarchical Gaussian filter, well, it may not be a problem, but it certainly takes you into a different sphere, is that it's usually formulated, the volatility is usually formulated in continuous time using autoregression models, which is fine, but it just destroys the sort of Markov decision process aspects that you get when you're using discrete state space models with Markov decision processes. But it would be, if you like, the grown-ups way of modeling volatility. You know, if you wanted to do that. The people doing this, well, obviously Peter's here, so it's the Aarhus group that is centered around Chris Mathis in Aarhus. But also Andrea, Peter, how do you pronounce the second name in Toronto?
Andrea Diaconescu?
Correct, yes. So she also is, and you might want to look at her work. She's been looking at sort of go, no-go tasks using active inference, but also is a little bit of an expert. She's actually on this one, an expert in applications of the hierarchical Gaussian filter in computational psychiatry. So there is a community. I think there are several hundred papers using the HGF in one setting or another.
They all come out of Clash Defense Center originally.
Okay, fine.
So
Yes.
Andrea used to work there, and Chris was his PhD student, and so on.
I see what you're saying. Yes, although Klaus himself, does he actually use the HGF anymore?
We have some collaborations with his group. Yeah, he does, but I would say he's maybe more focused on the neuroimaging modeling.
Yes, and self-efficacy and fatigue and the like. Yeah. So just a nod to that. So I was going to promise to speak quickly, but I'm not. As my apologies. So things that are to my mind, the best work in terms of computational phenotyping, and I'm just putting this up as the original description of computational phenotyping behavioral called cognitive modeling under partially observed Markov decision processes. I think it was done by Philip Schwartenbeck. He's now left science, but in terms of a rule book or a copybook of how to do this, how to use active inference to model dopaminergic function, and then translate that into an fMRI study, in the most mechanistic and insightful way. I would just go back to this very early literature, which must be about 10 years old, almost exactly 10 years old now. So Philip was the first author on the proof of principle, a tutorial as to why and how you should fit active inference models to behavioral data, and then went on to use, I think, actually the toy example in the computational phenotyping paper to then interpret his fMRI paper in terms of testing hypotheses about the particular role of dopamine in encoding, in this instance, the precision of beliefs over policies. So to my mind, this was a sort of foundational sort of demonstration of what you could do, and just reminding me largely of that literature because it's now getting quite old. The other point I thought you might quite like is you sounded as if you needed to justify using the state prediction error proxies as the KL divergence. I think you should feel fully licensed in doing that. There is a sort of notion in neuroimaging that all we are doing whenever we measure an fMRI brain activation, or we have a change in the power, the squared amplitude of an invoked response or the power of induced responses, all that we are doing is measuring the KL divergence associated with updating a prior belief, intra posterior belief. And you could even argue that from first principles, if you really wanted to, that if you just go right back to the physics of belief updating, erasing information, and the Landauer's bound on the thermodynamic cost of that, there are sort of principled reasons why the amount of belief updating, as scored by the KL divergence that you're using, costs a certain amount of energy or requires a certain amount of work. and we even know that the expressions via things like the Jasinski equality that scores up. So I think if you're ever quizzed about why did you use a KL, you just say, well, this is at the end of the day, the best measure of any metabolic or thermodynamic work required for belief updating. And by belief updating, I simply mean changing your mind, updating your prior to a posterior in the face of some evidence. And you can show that quite convincingly using synthetic data. So here's your KL, your state prediction error, I think you called it. Personally, I generalize it. It's just the amount of belief updating, or the sort of some people call it Bayesian surprise. And here's the expected power of synthetic EEG responses, local field, showing a beautiful linear relationship. So I'm just putting, there is a little bit of a narrative maths in the discussion of this. Should you want to substantiate your justification of this particular kind of state prediction error, and that comes from a treatment of active listening. The application to then is irrelevant, but the discussion and the simulations, I think, are more generally useful. And so finally, oh no, we haven't got there yet. No, and another endorsement is this notion of looking at movement in parameter space as a way of characterizing and summarizing, very much in the spirit of generative embedding, the effect of drug interventions or diagnosis, visualizing it in a way, but also capturing the right space within which you can phenotype certain behaviors or certain generative models, implicit generative models. I show this because it's one of my favorite examples where it's been used in the context of epilepsy research. So there are two parameters, and they speak to the excitability of different neuron populations, and just tracking parameter, the movement through parameter space as a seizure starts. And of course, once you've got this parameter space, you can now start to draw separatrices or lines in it that if you cross from this part of parameter space to this part of parameter space, you've now become schizophrenic, or you've become sedated, or you've become this or that. So you can actually have sort of domains, as in a phase diagram, on your parameter space, which can be extremely intuitive. And you've got the right space because these are the parameters of matter in terms of generating the dynamics or the physiology or the behavioral question. So this, I repeat, it came from work by Richard Roche on, in this instance, the effect of NMDA encephalitis, I think, or, well, no, the effect on the excitability of various populations and how they fluctuate over time to produce seizure activity that can then be characterized. Right, and finally, so this is another thing you could do if you had your own PhD student and another year to spare. There is another way of doing all of this, but it does require you to leave the world of reinforcement learning and reward learning behind completely. And this way of doing it is not to cast the context reversal as a learning problem, but as an inference problem. And you actually stated that in your discussion that as soon as I get an incorrect response, I can infer immediately the context has switched. This is not a learning problem. This is an inference problem. So how would you write that down in an active inference setting? Well, you wouldn't have successive trials where you're carrying over your Ds, certainly not in the form of Dirichlet counts. So there is no learning here. There's no forgetting rates or learning rates. It's just belief updating. So every trial now is just the next step in a very long simulation. So if they've done 24 trials or 64 trials, you will be iterating your belief updating scheme for 64 trials. And as you're going along, you will be inferring what the probability of a transition from context 1 to context 2 is. And that context will interact with the actual stimuli at hand for this particular trial that will determine the most likely response to the expected free energy, given you prefer a correct response. And then what you can do, now what you've got is a setup where you've got online inference under the assumption that each subject has in mind, as part of their generative model, that the context can reverse. So there's only two contexts here. And of course, human beings have this. So this is not like a mouse study of reversal learning. You can't do that with human beings. Human beings know that the experimenter is going to play tricks on them and they're going to switch things around. So that's just something that needs to be inferred. And they just take the evidence that they've got it wrong as evidence that the context has switched, and that switch will be immediate. And it'll be an interesting switch because there'll be a Bayesian surprise or a state prediction error or whatever, which you can measure. But so notice now, how are you going to get sort of differences in that switch? And where is the role of neuromodulation in this game? And at this point, you start to think about well, what is in active inference literature? What does neuromodulation do or encode? Well, it normally encodes the precision of things. So what things can have a precision in a straightforward active inference implementation of this trying to get correct responses in a context switching paradigm? Well, you can either have precision of your likelihood of mappings, or you can have precision of your transitions. And there will be different kinds of transitions. It could be the transition from, the current stimulus is the face outlined or the scene outlined, whatever. And there'll be other state transitions pertaining to the context that will be much slower. In the B matrix and the transition matrix, that much slower just means that 99.9% going to stay in this context, but there's a 0.001%, for example, going to be the other context. So the rate now becomes a function of the off-diagonal switch from context 1 to context 2. And in fact, there's a really trivial expression for the rate. And of course, that is also the precision. So the rate at which you expect the context to change, namely the volatility, now becomes encoded in the precision of the transition probabilities for the context, not for everything else that can change very, very quickly. You may start off, there may be a 50-50 jump from the face outlined to the house outlined on every new presentation of the cube, for example. So, that will be a very imprecise transition that accommodates things that change very, very quickly. But the context will change quite slowly. And that means that the B matrix or the transition dynamics of the B matrix is, has a precision that encodes the volatility in the form of a Peter?
I didn't want to interrupt. I just had a question.
Right.
Would you put learning on the B matrix for the context transitions?
Well, that's what we're coming to. Yeah.
Okay, sure. Good. Sorry.
Yeah. But before we go there, so where does that transition come from? Well, yeah. Before we go there, let's just stand back and just think about, well, if I'm now trying to understand everything in terms of belief updating and Bayesian surprise and being a good little inference machine, how can I put some sort of pharmacology on this in terms of modulating neurotransmitters? This paper by Thomas Parr has a table in it, which I won't bother finding it, that basically provides the evidence, which has been rehearsed a number of times, and also nicely reviewed, I think, by Kenji Doyer and to a certain extent Angela Yu and Peter Diane subsequently, suggesting that cholinergic neurotransmission changes the precision of your likelihood mapping. Noradrenergic transmission changes the precision of your dynamics, of your B matrix. And dopamine changes the precision of your policies. So what does that mean? Well, it means that if it's the case that the precision that matters in terms of encoding, representing, and acting upon the volatility or the frequency of context switches rests upon the precision of the transition matrices, we will predict on the basis of this kind of treatment that you're looking at here, that this depends or is reflected in noradrenergic discharge and not dopaminergic discharge. So you'd expect that something that something like methylphenidate that blocks both noradrenaline and dopamine will have an effect, but sulpiride would not.
Yeah.
Yeah. Because, well, that's not true. It depends to what extent. There's an interesting little twist here, which, again, if you had a PhD student an extra year, you can get into. Because when you change the precision of your transition dynamics, because you're planning, you're rolling out into the future, then your expected free energy also changes its precision. Because you're less certain about what's going to happen next. So if I think that the context is going to change very, very quickly, when I plan to even my next step, I could lose confidence in what the obvious thing to do is, simply because I've lost noradrenergic. So there'll be a coupling between the dopaminergic precision over policies and the adrenergic effect. So in fact, if there was a reactive, if you actually modeled the precision as a random variable, there probably will be a coupling there, and you would now posit a coupling between dopaminergic and noradrenergic on this very simple, clean model of where do neuromodulators modulate the precision of this sort of ABC construct of belief updating. So that would be, if you like, purely theoretical introduction to a paper which takes a completely different approach from the reinforcement learning people. This is pure belief updating, and takes a 21st century view of and very specific 21st century view of neuromodulators as encoding precision. And then the obvious question of what? Well, the only things that, then you have to list all the things that can have a precision, and then you go for the likelihood, and so on and so forth. So that would be one way of doing it. But let's come to the final point, which was your question. So where's the learning? The learning could be in terms of Dirichlet parameters, or it could be on the updates to the precision themselves. So this paper, the reason I put this paper up is I think if you did have a spare PhD student and another year, you would enjoy reading this, because it does actually address a similar kind of problem to the problem you're dealing with, which is uncertainty, volatility of a particular kind in terms of checking the world hasn't changed in this instance by actually not saying correct or incorrect, but actually looking at different parts of the visual scene. But it's the same structure, the same kind of problem, and unpacks it in terms of the generative model. But the key thing is that it is the only paper that I'm aware of that actually derives the updates for the precision parameters. Yeah. So now, instead of having a Dirichlet parameterization of your A and B matrices, you have something called a Gibbs parameterization. And the Gibbs parameterization effectively has like a softmax function or an inverse temperature that is the precision. And now you can work out what your free energy minimize, what your update. So this now gives you an opportunity to actually look at the belief updating about the precision that should be reflected in the fluctuations in the neuromodulatory discharge systems. And then there are a number of different, I think the precision parameters are then associated with the different neurotransmitters. And I'm hoping there was a table which, it's not, my apologies. There is another paper where he has a table linking the, oh no, here we go. Yeah, a really simple little. So it's got now 3 kinds of precision parameters associated with the sort of A, B, and C likelihood mappings, transition dynamics, and planning or policy or behavior, yes, policy precision, and then shows you how to derive these. Now, Chris won't have access to this, but Thomas may have the code that implements this. Should you want
Oh, cool.
to go through it?
I really like the idea of modeling it this way. It's like very elegant. Yeah, I like that a lot.
Yeah, it does have the disadvantage that you can't now appeal to the Dirichlet accumulation literature. But what it does do, instead of just having ad hoc scholar-like sort of updates, or the kind of learning rate parameterization that Ryan's put in, and indeed is there as a sort of hyperprior in the SPM code. As you say, it actually is now an update equation that is free energy or self-evidencing. But you can't use the Dirichlet form anymore, simply because you now have a different kind of parameterization, which is explicitly in terms of a precision for this matrix. So you've got this global precision parameter that now can be updated. And my guess is that this would be an elegant way to now have another two. Yes, I think it'll be 2 or 3 parameter, because you can now get your dopamine in, because if you model the planning to say correct, my prediction is this or that. You've now got, and that depends upon whether I think the context is going to change on the next move. So you now have an opportunity to do 3 parameters should you want to, and you put cholinergic stuff in as well for the likelihood. Although I'm not sure what sort of methylphenidate does to cholinergic. Sulpiride might have an effect. I don't know. Anyway, so that will be one way to proceed. But it would be it'd be power user, very bespoke, because as I say, it's only Thomas Parkes really taken this forward, and then he had to leave the field to complete his training as a neurologist. So it would require some commitment to pick it up again and start to make it work in the context that you're considering. But these would be the, if you like, the replacements for your state prediction error, learning and unlearning and forgetting equations, which are, they are a little bit ad hoc, although can be formally justified by the HGF and also other approaches. Sorry, Peter?
Yeah, I wanted to, I suppose if Beth does not use the Gibbs parameterization, the rest is quite straightforward, right? The context switching, if you put a bit of learning on that.
Yeah.
So implementing that part and fitting it shouldn't be too complicated.
Yeah, that's exactly that's what I was going to end up by saying, that you can, and certainly the current SPM version of the active inference schemes does online learning and does online Dirichlet accumulation. And then but your parameters now are they may actually now reduce to the same kinds of parameters that you've already implemented. But now you've got a choice, because you can actually measure the accumulation of Dirichlet counts in the B matrix and measure the precision of the B matrix and say, irrespective of the actual implementation, I think this is going to be reflected in sort of neuroadrenergic tone, that itself is going to be at the end of the day, at the end of this session, or over the entire session, changed by the drug status, the drug intervention. So you don't actually have to use if you use a Dirichlet parameterization, there is no, if you like, precision parameterization. You have a learning rate of the Ryan-Smith kind, which which would be an important parameter, because that sort of implements the forgetting, as it were. Just for your interest, the way it's currently implemented, that forgetting thing is actually parameterized as how many instances in the past do I keep in mind as relevant. So you can always interpret the learning and forgetting rate as basically just looking at the past 12, 8, 16, 64, 512 instances. And so now it's specified in terms of how far into the past do I go, which of course, is a hyperprior on the volatility. If I think the world is changing very, very quickly, then I'll just look in, I'll just retain a few and it's actually parameterized like that. So it still has a role and would possibly be a really important parameter to optimize when you're sort of fitting it to actual empirical subjective data. The thing that interests me though is that if you use the Dirichlet belief updating and accumulating with a little bit of forgetting, the volatility matrix, which is now your B over the context switching, you've now got this interesting situation where you can now vary the initial priors, which is basically how impressionable is this subject. So if you've got very small Dirichlet parameters at the beginning, and then you accumulate them, you become more and more confident in the transition dynamics. So you get this interesting situation where you can come really, really, really precise and confident that this is completely volatile, imprecise environment. And this is what Peter was talking about before, that you got this sort of meta confidence that I know nothing is predictable. And of course, you accumulate that with the experience, and that's this sort of meta learning. This is a sort of learning what is learnable and what is not learnable. And of course, subjects may differ depending upon where they start. If they start with a sort of hyperprior, with say 24 Dirichlet counts on staying in context 1 and say 8 in staying in context 2, which means they think it's going to be quite a volatile environment. As opposed to just having 1 in staying in context 1.5 and moving to context 2. They're going to be quite stubborn and they're going to learn quite slowly before they accumulate enough relative Dirichlet counts to overwhelm the 28 versus 6, for example, they've already got. Or if they're really old and stubborn and grumpy, they could have 1,000 and 600. And of course, you've got to have at least 1,000 observations before you make any difference to that ratio. So you've got this interesting notion of now phenotyping any given subject in terms of their prior convictions about the volatility of context switching. So young people might come in and say, I have absolutely no idea how naughty the experimenter is, so I'm going to start with really low Dirichlet counts and learn quite quickly. Other people might come in and experienced experimentees in psychophysics and know exactly how volatile it's going to be because they know how long the paradigm is because you're paying their expenses. And they will have very precise beliefs, and they're not going to learn very much from the switching. So that'd be another interesting way of phenotyping each subject in terms of their prior beliefs. That they can then accumulate and forget. So you could argue that over the 64 there should be no forgetting. In terms of the volatility in and of itself not changing, you could just have them not and just accumulate from the beginning to the end of a particular session. This is the volatility of this session, and I'm going to grow my Dirichlet counts until I get a good estimate of the transitions or the precision, and just use that as a sort of proxy for and assume that will in some way be reflected in noradrenergic discharge or dopaminergic discharge. And as such be a good proxy for sort of the effects or targets for the effects of sulpiride and methylphenidate. So you don't have to have forgetting. Especially over short trials, but just use the actual precision of your transition dynamics of your volatility beliefs about the volatility as the the score of the differences between subjects. The slight problem with that is you can't really put that easily. Well, I suppose you could put that in on a parameter map, but it's not actually a parameter. Unlike this model here, here you've actually got dopamine and noradrenaline as parameters in the model, and they have their own free energy minimizing dynamics. But it's still an interesting question about sort of the impressionability of the subjects in terms of their beliefs about the volatility or the tendency of the world to change very quickly, and immediately gets, point towards things like jumping to conclusions and schizophrenia on certain conditions.
Yeah.
These are all ways of or priors, different kinds of belief updating that speak to how impressionable you are, and this all rests upon your priors. Anyway, I said I'd talk quickly, and I have been talking quickly, but I've also possibly been talking too much, so I'm going to stop talking now. And thank you for your attention.
And can I just
Peter,
add,
yeah, you go.
I just wanted to add very briefly that the Gibbs parameterization Carl just showed, I've actually, on a little side project with Brennan at some point, implemented those equations.
All right.
But without a deeper understanding at the time, I was reading off the implement. But just to say that, Beth, that if you do get an extra PhD student and an extra year to help out or something, because
Cool.
it's something I wanted to implement in my own software anyway.
Oh, awesome.
Good
Cool.
reason. Yeah. But no more words from me now. Sorry.
Thank you so much. That was so helpful and insightful. And even though it's 3:30, I still feel like I learned a lot. So that's
I think it's time for bed, isn't it? Well, thank you very much indeed.
All right, thanks, guys.
Then I suggest we quickly give Beth one last round of applause. Thank you, Beth.
Thank you.
All right. Thanks everyone for coming. Sleep well, Beth. We'll get there.
All right. Bye.
Bye-bye.